Okay, this is lesson 1.5b, the inverse function and its properties, but this time instead of graphically, we're looking algebraically. I need you to recall first that the notation for an inverse function is f to the exponent -1. That means f inverse of x. And f inverse of x reverses the original function so that it undoes what the original function has done. The inverse, f inverse of x, is only a function if it passes the vertical line test or the original function passes the horizontal line test. In the case of the quadratic and the absolute value functions, where f inverse of x is not a function, we can make it a function if we restrict the domain of the original. And we'll look at a couple examples of what that means. First, what we're going to do is we're going to determine the equation of the inverse function. And the way we're going to do it is similar to how we did it graphically. We're going to swap the x and y, just like we did when we were showing points changing on a graph. We would flip the x and y and make it a yx point and then regraph it. We're going to do that in the equation too. And then we're going to isolate for y. So I'm going to show you a couple examples. Oh, sorry, first. What it means to be an inverse. So in words, if we had a rule to represent the inverse of this function, f of x equals 4x plus 3. In words, what that would mean is it would be the opposite operations in the opposite order. So the operations on x are multiply by 4 and add 3. And it would be done in that order because that's BEDMAS. To undo those operations, we would have to undo these in the opposite order. So instead of multiplying first and then adding, we would first subtract and then, instead of multiply, divide. And basically, these are just the steps to isolate for x. But as a rule, f inverse of x would say subtract 3 and then divide by 4. So let's see what the inverse actually looks like. And here we have a graph. This is the original function f of x. And we know that because it has a very steep slope of 4 and a y-intercept of 3. And this is actually our inverse, f inverse of x. So here we go. Determine the inverse of the function f of x. Here's our f of x equals 4x plus 3. We're going to replace the f of x with y to make our notation a little bit easier. And then we're going to swap x and y. And when we swap y, we're going to change it into y inverse. And now we're going to isolate for y inverse. So to do that, we need to subtract 3, move the 3 over, and then divide both sides by 4. And that gives us y inverse is x minus 3 divided by 4. And if we look at the rule we came up with, well, the rule was subtract 3, divide by 4, and that's exactly what we're doing. X, subtract 3, and then divide your answer by 4. And since this is a function, we're going to designate it with function notation. So we're going to say,
good morning to all staff who have not signed in. Please come to the office and do so. Thank you.
So we're going to say f inverse of x equals x minus 3 over 4. And that's just the equation of a line. This time the line has a much flatter slope. It'd be 1 over 4. And the y-intercept would be negative 3 over 4. And we can see that there, negative 3 over 4 and a much flatter slope. Let's try another one. Oh, sorry. What do you notice about the slopes of f of x and f inverse of x? So let's write that down first. The slope, sorry, this is for f of x. The slope would be 4. And for f inverse of x, the slope would be 1 over 4. So what do you notice about these two numbers, 4 and 1 over 4? Well, what you should notice is that they are reciprocals. Second question, are there any invariant points An invariant point means, are there any points on the graph that don't change when you reflect it over the y equals x or when you find the inverse? And we have one invariant point. It's where both the function and f of x cross. So we have yes we do. We have one point. And that point, if you read the coordinates, is -1, -1. And what's significant about that point is on the line y equals x. In fact, if you have a function and it crosses the line y equals x, it's going to be an invariant point when you change x and y, because every point on the line y equals x would have the same x and y, right? If x was 1, y would be 1. If x is -1, y would be -1. Invariant point just means it doesn't change. It's variant means change, so it changes. Invariant would be the opposite, so it doesn't change. Any points that don't change when you take the inverse, yes, there's the 1. All right, now we're on to the second function. F of x is equal to -x squared minus 2. And if we look, we have two graphs here. Which one would be the original? Well, this would be the original f of x, because this is a parabola that opens upside down and starts at the vertex -2. And if we drew on the y equals x line, we'd see that this is a reflection over that line. So this is going to be our inverse. So let's find the inverse. Same strategy. Replace f of x with y. Switch x and y, and turn y into inverse. And you have to be careful here. This is not an exponent. Even though I referred to it as an exponent when I was describing the notation, you can't multiply these exponents. This is saying y inverse. It has nothing to do with the exponent on y. So when we're isolating, we're not multiplying these exponents. So be careful of that. So let's start isolating. We can add 2 to both sides. We get x plus 2. We've got a negative in front of a bracket that has y inverse in it, and that bracket is squared. Now we need to undo this negative. The opposite of this is like -1 times. So to undo it, you could either multiply both sides by -1, or you could divide both sides by -1. I'll divide. So let's divide by -1. Dividing by -1 gets rid of the negative sign. So now we just have y inverse squared. And over here, 1x divided by -1 would be -x. And 2 divided by -1 would be -2. And one last step, to get rid of a squared, we could square root both sides. And something interesting happens here. When you square root, you're actually going to get 2 answers. You're going to get a plus and a minus answer. So we get a positive and a negative, and we're square rooting. -x minus 2. Writing the plus minus in front of the square root is pretty important, because what it means is, if we look at our sideways parabola here, that's our inverse function. For every x, we're getting 2 y's. So like x of -4, we're getting a y up here, and we're getting a y down here. And the reason we're getting 2 y's is because, well, let's look at the equation. If we input -4, we'd get -4, which is 4, minus 2, which is 2. Square root 2, you get both plus and minus answers. That's why we get an answer up here and an answer down here. Now, this isn't a function. If we wanted to make it a function, we'd have to put a restriction on the original so that when we reflect it, we get a function. And since this function doesn't pass the vertical line test, horizontal line test, the inverse won't be a function. So using function notation here would be wrong. But if I wanted to make it a function, I could choose either the top or bottom branch, the positive or the negative answer. Conventionally, we usually choose the positive answer. So we would say like f inverse of x equals the square root of -x minus 2. And this implies that we're only taking the positive answer, and therefore we would get just this branch. And I missed the curve there, but if we wanted to call it a function, we would be getting just this branch. If we didn't want to call it a function, we just wanted the inverse relation, it would be the entire sideways parabola, and we would just call it y inverse. All right.
Mr. Hagerman, please call extension 103. Mr. Hagerman, 103.
C. F of x equals the square root of 5x minus 7. We're going to find the inverse equation. On our graph here, we have our f of x, that's the original function, and this represents our inverse. So we're going to work through this one a little bit quicker. I'm going to go right into finding the equation algebraically. I'm going to replace f of x with y. I'm going to swap x and y. And now I'm going to start isolating for y inverse. To isolate for y inverse, what would I have to do? Well, I would square both sides. If I square the right side, I'd be getting rid of the square root. And if I square this side, I get x squared. So now we have x squared equals 5 y inverse minus 7. And now I add 7 to both sides. We get x squared plus 7, 5 y inverse. And now if we divide both sides by 5, we get y inverse is x squared plus 7 over 5. And what we have here is a relation that's quadratic. But if we look at our function, we don't have an entire parabola. We just have part of a parabola. And the reason why is because there's a restriction on the original function that says it's only the positive root. So we have only this branch. So what's that mean about our inverse? Well, there's a restriction on our inverse function. Our inverse function is x squared plus 7 over 5. But it only exists when x is greater than or equal to 0. It only has this part of the branch. So we would say x must be greater than or equal to 0. And this shows us that we have a function that's quadratic, but we only have the one branch. And the reason why is because if we look at the range of the original, it's nothing, or the function doesn't go below 0. The range has a restriction. The y has to be greater than or equal to 0. And what we learned about inverses is that the domain and the range flip. So if the range of f of x is that y is greater than or equal to 0, the domain of f inverse would be x is greater than or equal to 0. So we have a restriction, and that's why we only have part of a parabola, even though the equation looks quadratic. All right, and D. I'm going to make one of these darker so you can see which one's which. This one's a little trickier to tell which is the original function and which is the inverse. Not super worried right now at this point if you can't tell which one's which. We have to work a little bit more with transformations still in this unit for you to figure out which one's which. But the darker one here is f of x. And the lighter one is f inverse of x. If we want to find the equation, well, let's do it. Let's make f of x y, and let's switch x and y. Let's isolate for y inverse. So we're going to subtract 1 from both sides, and we get x minus 1, 3 over 2 minus y inverse. And now the y we're trying to isolate for is on the bottom. To put it on the top, we'd need to multiply both sides by the bottom of the fraction. And if I do that, I get this. And if I want to start isolating for this, I need to get rid of this bracket on this side, and to do that, I could divide. And what we have is that 2 minus y inverse is equal to 3 over x minus 1. that step that I just did here, if we look back over here, basically what we've done is we've taken this term and swapped it with this term to end up here. It's kind of like cross multiplication, even though that's not really a thing. That's something you might have heard of before. That is basically what we're doing here. We're multiplying both sides by the denominator to put it in a numerator on the other side, and then we're dividing both sides by the term we don't want, and that puts it in the denominator on the other side. And now to finish isolating, I'm going to take a step here. This is negative y inverse. I'm going to move it to the right side to make it positive. So we got y inverse, 2 stays, and I'm going to take this entire term, because this is just like a fraction. I'm going to move it to the other side by subtracting it. And there we go. Now we have a inverse function. And if I write it using function notation, we have f inverse of x is 2 subtract 3 over x minus 1. And there's our inverse function. All right, that's lesson 1.5b, inverse functions and its properties algebraically. Thanks for watching, and I'll see you next time.